Okay, so in this video, we will consider 4 special summations. Now there are several special summations in the theory of summations. In this video, we'll consider only 4, and those will be the summations that will be useful for us when calculating the area under a curve of a polynomial up to a degree 3 polynomial. And these special summations, why do I use the word special? What is special about them is we have shortcut formulas. So we will not have to evaluate the sum by adding up every single term, but instead shortcutting the sum into a final, very simple formula. So let's start with the first one, the simplest one. What if I sum I going from 1 to n? So here again, n is an integer. I goes from 1 to n, so I will be 1, then 2, then 3, up to n. What if I sum 1? Well, let's expand. When I is 1, 1 is 1. So it's 1. Plus, when I is 2, 1 is 1. So plus 1. Plus, when I is 3, 1 is 1. 1 plus, all the way up to when I is n, 1 is 1. 1. So what do we have here? 1 plus 1 plus 1 plus 1 plus 1. How many times? Well, as I goes from 1 to n, that consists of n terms. So we are adding 1, quite simply, n times. But if you're adding 1 n times, all you get is n. So if you're ever summing 1 from 1 to n, don't do 1 plus 1 plus 1 n times, just say it's n. So you see, first shortcut formula. Very simple one, but we're bypassing the sum. We're not going to do 1 plus 1 plus 1 n times. We're going to say if you sum 1 from 1 to n, it's just n. Alright. You might think, well, this is not so interesting. Well, let's make it more interesting. Instead of adding up 1, let's add up I. Let's expand this. And I'll give this a name. I'll call it S, and you'll see why in a second. Well, Sn, I should say, because we're summing up to n. So let's see what comes out of this. When I is 1, we get 1. Plus, when I is 2, plus 2. Plus, when I is 3, plus 3. All the way up to plus I being n, plus n. So you see why I'm calling this Sn. It is the sum of the first n positive integer. So if n was 7, it'd be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. The question is, can we evaluate such a summation for any n without having to add every single term? And the answer is yes. And we'll have to be a little crafty about this. So let me rewrite it here. So Sn, the sum of the first positive integers, 1 plus 2 plus 3 up to n. Now, notice that we are summing n terms. Let me rewrite Sn, but now by summing the terms in a completely different order. Instead of summing from 1 to n, I'll sum from n down to 1. So I'll do n plus, well, what's before n? It would be n minus 1. Plus, well, what's before n minus 1? It'd be n minus 2. Plus, dot, 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 all the way down to 3, 2, 1, 1. Exact same sum, but written in the opposite order. Right here I'm doing 1 plus 2 plus 3 plus 4 up to n. Well, I can do it backwards. I can do 1 plus 2 plus 3 plus 4 up to n. And then you might ask, well, why am I doing this? Well, what I'll do is I'll add both together. So if I do Sn plus Sn, that's obviously 2Sn. And the question is, well, how do we add up these now 2n terms? We'll add them up in pairs. So if you add up n with 1, you get n plus 1. Plus, Then we'll add up 2 with n minus 1. But n minus 1 plus 2 is again n plus 1. Plus, we'll add up 3 with n minus 2. But once again, n minus 2 plus 3 is n plus 1. You can probably see where this is going now. Plus, 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 plus. Finally, the last two terms end with 1, but n plus 1 is again n plus 1. And you see, well, what we now have is trivial, right? We have n terms, n pairs. First pair, second pair, third pair to the nth pair. And every term is the same. The sum of every pair is n plus 1. So we are adding n plus 1 exactly n times. But if you're adding n plus 1 plus n plus 1 plus n plus 1 n times, that is just n times n plus 1. And look at the equality now. 2 times Sn is n times n plus 1 divided by 2, and you now have a formula for Sn being n times n plus 1 over 2. And this is fantastic. Why is this fantastic? Well, let's rewrite the Sn from its original sum. We'll write the expanded form, and then we'll write the formula. And hopefully you'll understand why this is so great. So Sn, the sum of I, as I goes from 1 to n, is the sum of the first n positive integers. So I equals 1 plus I equals 2 plus I equals 3, all the way up to I equals n. But now what we're saying is that Sn, this summation, is simply n times n plus 1 over 2. Let me just go back up and put this one also in a rectangular box. Although this one is very, very simple. If you add 1 n times, you get n. That's it. This one now is really interesting because think of why this equality is so neat. Suppose I give you n equals, let's say 100. And I say evaluate this sum. Then you'll do 1 plus 2 plus 3 plus 4 plus 5 all the way up to 100. That's a lot of terms. You're adding up 100 terms. If you use this form, it's just 1 multiplication, 100, times 101 over 2, and you're done. So this is really, really easy to calculate. It takes no time. This one takes quite a lot of work. So this is our first shortcut formula. So if you ever need to add the first n positive integers, don't brute force add them up, use the formula. Let's look at two simple examples to really emphasize why this formula is just so nice. Let's start with an easy one. Let's go with 10. So this one we'll do both ways. We'll do the long way and then the short way to make you really appreciate why this formula is so nice. Alright, long way first. So we're adding I as I goes from 1 to 10. So this is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. Alright, let's start adding. 1 plus 2, 3, plus 3, 6, plus 4, 10. 10 plus 10 is 20, so we have 20. Then 5 plus 6, 11, plus 9, 20. 7 plus 8, 15. That takes care of everything, and we're left with 40 plus 15, 55. So if we add the first 10 positive integers, we get 55. This was brute force adding up the 10 terms. It was not too bad. Let's see if we can do better with our shortcut formula. We are summing I from 1 to 10. And now we can bypass the sum, not do this, right? This is sum from 1 to 10, and we're summing I. Now here n is 10. So if you're summing I from 1 to 10, the formula says don't add up all the 10 terms. Plug in n in here. So we'll get 10 times 10 plus 1 is 11 over 2. But this is not trivial. 10 over 2 is 5. 5 times 11 is 55. Voila! So you see this was much slicker than finding the sum brute force. And you might think, well, this was not too bad. You know, adding up the first 10 positive integers. Now let's add up the first 100 positive integers. So what if, I'll put it here, we said now let's sum I as I goes from 1 to 100. Well, if we did this brute force, it would be 1 plus 2 plus 3 plus 4 plus dot 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 plus 99 plus 100. So adding up all of the first 100 positive integers, brute force. This I am not going to do. If you want to evaluate this sum brute force, knock yourself out, have the time of your life. I'm saying life's too short. Let's not do this. Let's use our shortcut formula. And here you'll really appreciate how slick of a formula this is when n is slightly larger. So again, we are summing now I from 1 to 100. With our formula, we can evaluate the sum bypassing the brute force sum and just plug in n in here. So here, n is 100, so we'll have 100 times 100 plus 1 over 2. Well, let's see. 100 over 2, that's 50. 50 times 101. Well, let's break this up. 50 times 1 is 50, plus 50 times 100 gives you 5,000. So in the end, it's just 5,050. And we're done. It took us, what, 10 seconds? And now, this is the answer you would get if you would do by hand. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 all the way up to 100. If you do this sum brute force, you will arrive at 5,050. Of course, this will be much longer. So hopefully with these two examples, you appreciate why this shortcut formula is so nice. So we would never evaluate the sum directly. We would always bypass it with the shortcut formula. Let's look now at two similar formulas if we're summing I squared and I cubed. Now those two formulas are more challenging in terms of deriving them. You see, coming up with the formula for the sum of the first n positive integers was actually clever. It was not obvious, but it was fairly straightforward. Now the other two sums are much more challenging to tackle, and so I'll just give you the results. Okay, so and I'll put a summary box here. What we have so far, if you sum 1, I going from 1 to n, this is simply adding up 1 n times, and all you get is of course n. Kind of boring. Second sum, the one we've just derived, this one is interesting. If you sum now I from 1 to n, you get 1 plus 2 plus 3 all the way up to n. Now we know better not to evaluate this sum directly, but to use the shortcut formula as n times n plus 1 over 2. Let's go up to I cubed. If you summed, now I ranging from 1 to n, I squared, well, you would get the sum of the first n positive squares. So 1 squared plus 2 squared plus 3 squared up to n squared. And again, if you ever have a sum like this, the sum of the first n squares, you would never evaluate this sum directly. You would instead use this shortcut formula, which is n times n plus 1 times 2n plus 1 all over 6. And as I've said previously, this is far from obvious. To derive this formula requires much more work than to derive this one. So I'll just give you the result, and then I'll show you one example to at least convince yourself that this works for a given value of n. And we have a similar formula for the sum of the first n cubed, so summing I cubed. Now this will be when I is 1, 1 cubed, plus when I is 2, 2 cubed, plus when I is 3, 3 cubed, all the way up to when I is n, n cubed. What's nice about this one is it's just the sum of I from 1 to n squared. So it's really easy to remember. N times n plus 1 over 2, and you square the whole thing. And that is your shortcut formula for the sum of the first n cubes. Once again, this formula is far from obvious, so we won't derive it. But let me now give you just a simple example of each of these two sums for a small value of n to at least check that the formula works in these two simple cases. So these 4 formulas, you will be expected to remember the shortcut for these 4 summations. So never add any of these sums directly. Use the shortcut formula. Alright, let's consider now an example of our last 2 summations. Let's sum. Let's go to the first 5 squares. So we'll sum I going from 1 to 5, I squared. We'll evaluate the sum brute force, then evaluate the shortcut formula. So this would be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared equals, well, 1 if we square plus 4 plus 9 plus 16 plus 25. Let's add these in a smart way. 1 plus 9, 10, plus 4 plus 16, 20, plus 25. So what are we left with? 10 plus 20, 30, plus 25, 55. So if we add the first 5 squares, we get 55. Well, let's plug in the formula and see that we get 55 again. Well, this is the sum of I squared, I ranging from 1 to 5, so n is 5. Let's plug in 5 in this formula. So we'll get 5 times 5 plus 1 is 6 times 2 times 5, 10, plus 1, 11. And all of this is divided by 6. Cancel the 6 over 6, and of course that leaves you with 5 times 11, which is 55. Check. This is not a proof. It's a check that this formula works for n equals 5, but it does work for any positive n. Let's look now at the cubes. Let's go up to, say just 3, as these are getting large very quickly. So we'll sum the first 3 cubes. First brute force, so this would be 1 cubed, plus 2 cubed, plus 3 cubed. Well, this is 1 if you cube, plus 8, plus 27. 1 plus 8, 9, plus 27 is 36. Let's evaluate now with the shortcut formula. Here n is 3, so let's plug in 3 in here. So we get 3 times 3 plus 1, 4, divided by 2. You square the whole thing. Well, 4 over 2 is 2. 2 times 3, 6. And 6 squared, of course, is 36. Check. Again, this does not prove that this equality is valid. It just shows that it's true for n equals 3, but it is true for any positive n. And now, of course, this is interesting when n is large. If n was 100, you wouldn't sum these explicitly. You just plug in 100 in both sums and both formulas to arrive at the final answer without having to sum 100 of 100 squares or 100 cubes. So again, really efficient shortcut formulas. Let me give you one last example of evaluating a sum that involves all of these 4 formulas and all of the properties of summations we've seen in the previous video. So suppose I said, let's evaluate I ranging from 1 to 12. Let's go with 2i cubed minus 5i squared plus I minus 4. And we want to evaluate this in the most efficient way possible. So of course you could be, naive here and say, well, okay, I'll plug in I equals 1. The first one would be, well, 2 times 1 cubed minus 5 times 1 squared plus 1 minus 4. Then plus this term when I is 2, so 2 times 2 cubed minus 5 times 2 squared plus 2 minus 4. Then plus this term when I is 3 up to 12. We're not going to do this. This is too much work. What we want is to use our properties of sigma notation so as to break this up into a sum of 4 terms, and we can then recover our 4 fundamental sums. So the first property says we can distribute the sigma notation over each individual term that we are adding or subtracting. So we'll first sum the 2i cubed. Then we'll subtract the sum of the 5i squared terms. Then we'll add the sum of the i's. Minus the sum of the 4's. And here I'll write 4 as 4 times 1. So first step, break up the single sum into 4 individual sums. Second step, let's get rid of all of these scalar multiples. These are constant multiples. And our first property was that we could move constant multiples outside of the summation. So let's do so. So we have now 2, moving it out. The sum, I going from 1 to 12, of I cubed. Minus, let's move the 5 outside. So minus 5 times the sum, I going from 1 to 12, of I squared. There is no multiple here, it's already the sum of I, so we leave it as is. We move the 4 outside, so minus 4 times the sum from 1 to 12 of 1. And if you look, by applying the properties of sigma notation, we have decomposed this sum into 4 sums, and these are all our fundamental sums. The sum of 1, the sum of I, the sum of I squared, the sum of I cubed. So we can of course now not evaluate each sum brute force by adding up the terms, the 12 terms, but by instead using these shortcut formulas. So here, 2 times, and we're all starting at 1, and we're ending up at n equals 12. So here, n equals 12. So I'll just remind you quickly of the formulas for the four sums, right? It is n times n plus 1 over 2, n times n plus 1 times 2n plus 1 over 6, and n times n plus 1 over 2 all squared for the four fundamental sums. And I will just use all of these four formulas when n equals 12. So the cubes, if you remember, sum to n, 12, times n plus 1, 13, over 2, the whole thing squared. Done. Minus 5. The squares sum to n, 12, times n plus 1, 13, times 2n plus 1. Well, 2n, 24, plus 1, 25, over 6, check, plus, summing I is n, 12, times n plus 1, 13, over 2, minus 4, and this one is the easiest. If you add 1 12 times, you get 12. And there you have it. Now you could, of course, simplify these expressions by hand and arrive at a final answer. And I will leave that up to you, as this is rather boring. What was interesting was to, using the properties, decompose the original sum into four individual sums, pulling out the scalar multiples, arriving at our four fundamental sums, and evaluating each one using the shortcut formula. Sum of 1 is n, sum of I, n times n plus 1 over 2, sum of I squared, n times n plus 1 times 2n plus 1 over 6, sum of I cubed, n times n plus 1 over 2, all squared. And that's it.